Hey everyone, thank you for joining us today as well as being part of the Analytics and Big Data Society. My name is Boyana. I work at Centelli Solutions, which is a data science consulting firm, and I also manage marketing and events for the ABD Society. Quick background about the society. For those who are joining us for the first time today, the Analytics and Big Data Society is a nonprofit organization based in Charlotte, which believes in the use of data for social good. The mission of the society is to establish Charlotte as a national analytics and big data hub. Throughout the years, we've been carrying this message through the various events we've been hosting, such as this monthly data analytics speaker series events in partnership with the UNCC School of Data Science. Thank you, UNCC, and also to all students who are willing to learn and are also attending our events. The ABD Society has hosts signature series events each quarter, which are on a larger scale, happening in person. Too bad that we had to cancel the first one because of the current situation. Hopefully in August, we'll get the opportunity to host it live and gather again. And lastly, our biggest annual event, the Queen City Hackathon, which was in February this year at the Red Ventures. This was actually our third hackathon. And we had over 250 participants. I believe the teams now are working on implementing or developing their solutions. So our upcoming event is June 18th. You can continue to follow us on our social media platforms, and don't forget to register on the upcoming events. In the meantime, I'd like to invite you to Centelli's Healthcare Fireside Chat on June 3rd. You can find more details on centelli.com. Obviously, I was not quick as I intended. I guess I'll be moving on to our speaker for today, Dima KOROLEV. He's head of machine learning at FriendlyData based in California. He has started with NLP and machine learning back in the day when it was called informational retrieval in 2005. After graduating, several events and several years at Google later, he switched focus and became an entrepreneur and consultant. His most recent gig was getting acquired as part of a small team, FriendlyData Inc., a company that has developed and productionized a high accuracy English to SQL solution based on strict grammars to parse the queries in natural languages. While he doesn't consider himself as an NLP expert, he enjoys speaking about the different approaches for the machines to understand the natural language, their strengths and weaknesses, and the future that lies ahead. Today, he will walk us through the formal and probabilistic approaches to pragmatically understanding the natural language. But before I hand it over to Dima, I would like to ask you to vote on a poll questions. You're gonna be seeing that on your screens. And we will be sharing the results at the end. Also, in the meantime, I would like to ask you to submit any questions that you have, and we're gonna address them at the end. All questions. Yep, there they are. So the first question is, do you think human languages are invented or discovered? The second question is, do you think machine translation would reach human levels soon? Third question, do you think OpenAI should have released their language model? And the fourth one, When do you think the machines will be able to appreciate human humor? I don't think that will happen, but I will leave it to you. Dima, you can go ahead. I believe you're on mute. Yep.
I think that worked. Thank you. Hi, Rishi. Well, first of all, a huge round of thanks to Rishi, to Bojana, and to Maitili for making this happen. I hope I will get some feedback from you guys during the talk. It's the first time I'm giving a talk over Zoom, actually. I've given talks online, but not over Zoom. So I assume that if it gets too boring, I'll get a hint from some of you, one way or the other. Well, given that it's not going to get boring, let's get started. Bojana introduced me extensively. Thank you so much, Bojana. So Rishi and I have met under different circumstances, and he suggested I talk about NLP itself. And you know what? I've given these talks before, and I realized your society is slightly more of a data scientist society. So you should speak some data science as well. So I'll make it a slightly more academic talk for the first part. So what is going to happen is, for the first maybe 10-15 minutes, I'll mention briefly what data science is about, in a sense that what actually do we mean by the data model, by the language model, by the model that generates text or analyzes text or categorizes it one way or the other. Because I think this part is often missed. In a way, it's a good thing that data scientists these days are more practical people who just know how to use certain tools to get the job done. But I think it's really worth it to spend 10-15 minutes talking about the true fundamentals. And then, since the talk is mostly about how to solve the real problems if you are a small company, since the field is getting more and more mature in the sense that it's really hard to catch up with companies that can afford to spend tons of money on the training data, on labeling data, on machine resources. So still we can compete. We can still do great things, either on top of what they have released or by taking shortcuts. And I'll mention those shortcuts too. And finally, hopefully we're going to get to intense Q&A. I'll tell you a secret. My fear, since I'm younger, is that I have a few slides which we go through in 10 minutes because it's too simple, and then it's nothing to talk about. That has never happened, don't worry. But all in all, I'm trying to make sure we'll get to the Q&A part. All right. When it comes to what data science is about, when I started doing that, it wasn't called data science. There was no such term, more or less. The many terms were there: precision, recall. We had models. We just didn't call them machine learning yet. And this fine gentleman is Claude Shannon. He introduced the idea of information as we know it in computer science. And he did it through the term entropy. If there are physicists here, you know that entropy is also a physical term, which measures the amount of chaos in the system. And right now, physicists have somewhat connected this to informational entropy. We'll not talk about this. I'm no expert to begin with. But the idea is that you can measure the amount of information as the amount of uncertainty. And the amount of uncertainty can be measured in how much data has to be transferred in order to eliminate this uncertainty. And Claude Shannon introduced the idea of bit. Bits are zeros and ones, but fundamentally it's just a logarithmic measure of the amount of degrees of freedom. So if you think about bits as zeros and ones, well, the English alphabet is, Latin alphabet is 26 characters. If you take log 2 of 26, it's about 4.5. If you add 5 characters of punctuation, one way or the other, space, comma, period, you name it, it's almost exactly 5 bits. Well, it's exactly 32 options, so it's exactly 5 bits. And the byte is 8 bits. But Claude Shannon asked, what's the informational density of English, of the actual written text? And he postulated this question way before we even had computers. I think it was over 100 years ago, almost 100 years ago. He conducted a really wise experiment, which I think it should be replicated one day these days. What he did was he took a random text, which is some piece of literature, and he didn't know this text, and he asked his wife to read this text to him letter by letter. And he was trying to predict the next letter. So you can think of him generating the probability distribution of the next letter. And the sooner it gets the right letter, the less information the next letter carries. So for example, if it's English, there is a lot of the article. So after T and H, you can assume it's going to be an E. So the information density of that E is quite small. Whereas if it's a new word, well, you never know. And what people tend to miss these days, even though it's so obvious if you started with this field 20 years ago, is that modeling information for the purposes of understanding is about the same as modeling for the purposes of compression. So in a way, text compression, this task doesn't even exist anymore because it's so easy to compress texts. But if you try to build a good language model, once you optimize this model towards capturing the meaning of text, you also pretty much train the model to compress text into minimum number of bits possible because, well, it predicts the next words and sentences, the next letters, words, and sentences of text. With this in mind, there actually is a good way to compress English text into fewer than 1 bit, well, fewer than 5 bits per character. And it's known as the Morse code. It's dots and dashes. And if you think about it, if you're hardcore computer scientists, this model is slightly imperfect. I have a better one, but it's harder to put on the slide. This model is imperfect because each node of this graph, of this tree, is both the leaf and the node. Because in the Morse code, you can transmit a character and then a small pause denotes that it's end of character. So you can pretty much think of it as a 3 characters alphabet, 0, 1 as in dot and dash and a pause. But the idea is that still, the more frequently used characters, such as E and T, are in the top. So there are fewer steps from the beginning of the letter. And because you can construct this tree in a smart way, you actually increase the density of information. So you can think about it as a language model, which is zero context, it's just letter by letter. But compared to generating letters one after the other with like 5 coin tosses, 1 of 32, if you use this model instead with coin tosses left to right, you'll get something that is still implausible as an English text, but closer to that, which is pretty much the first step towards OpenAI models that generate reasonable text, which is hard to tell if it's a human reading text or machine reading text. I just really feel it's important to understand how it all begins from 20 years ago and more. When it comes to compression, it's important to distinguish between lossless and lossy compression. Lossless compression is guaranteed to recover the same text. So Morse code is one simple example. I'm going to skip the Markov part, that's usually tricky, and let's take a huge step towards pretty much the modern day. We all know somewhat what does a language model mean. Let's say I have a language model for Shakespeare. So I take everything Shakespeare ever wrote. Hopefully I have more than just public data, like also letters and stuff like that. You can think of the language model of Shakespeare as the machine to both tell if something could or could not have said by Shakespeare, or you can think of it as a way to generate texts that sounds as if Shakespeare could have said it. In a sense, if you think about it, like forget computers for a moment. If take a Shakespeare expert, their mind contains some perception, some notion of what Shakespeare could and could not have said. And the more powerful their mind is, obviously they don't exist in a vacuum. They're humans. They have their own human context of the world we live in. They've learned the language by their own means. They read more than Shakespeare. So in theory, they could create phrases that Shakespeare could not have said because they use different words, for example. But they still have some notion of, is this phrase more or less Shakespearean? Similarly, if you think of the model in their mind as the model that a computer can apply, the way it works is this model will be able to compress Shakespeare's texts into shorter, well, with a better compression factor, with fewer bits per character, because this model, this particular human, can predict Shakespeare better than non-Shakespeare, and vice versa. Next to lossless compression, we have lossy compression, which means that you are allowed to, once you restore what you have compressed, you're allowed to make mistakes, as long as those mistakes are not noticeable or negligible by the observer, by the listener. And a good example of lossy compression would be music. 1 megabyte is about, I think, 500 pages of English text, and it's about 6 seconds of audio CD quality. I know this because I know CDs are 74 minutes. But if you think about MP3s, they are at least 10 times better. And with high quality MP3, you can still not tell the difference. It's because the human ear doesn't hear certain frequencies. So it's not essential to encode those frequencies as the digital data. As long as you as a human cannot tell the difference, you're good to go. The machine could tell that. You could build a physical machine or software that would tell the difference between an encrypted and decrypted MP3 versus CD quality. But it's still pretty easy to compress audio in a way that the human could not be able to tell the difference. And this actually translates well to, well, human perception and even texts. For example, if you were to record this conversation, record this talk, the actual words I'm saying are pretty low entropy. You have a language model in your own heads. You know I'm speaking okay English. You know what I'm going to talk about. So it's not too hard to construct the next word or sentence I'm going to say. The human connection part is in the nuances between, well, word pauses, intonations, my hand gestures. Video is also essential. And if you think about the evolution of, like, I hesitate to call them AI assistants, but if you look from Elisa many years ago to Alexa and Siri, they're getting more and more human-like and less robotic. There's such a term, robotic voice. And they are achieving this because they introduce more subtle details in the way they speak, even though those details are not factually important. That's what humans are. When you think about language models, it's the same problem. If it's just about making sure you can understand or generate perfectly grammatically correct sentences, that's a pretty simple problem. But we are way past it technologically. We can do a lot better because style matters, pacing matters, perception matters. Or for example, poetry. Poetry is a lot easier to predict, and it contains fewer bits per word because you kind of know what to expect. There are fewer options for the next word, especially if it's at the end of the line. And machines are somewhat doing this thing. If you think about capturing meaning in the technology like text embeddings, they're trying to predict what the next word, or in this case, the current word, would be based on the context. And this prediction is using some knowledge of the neighbors, of the surrounding, of the context of the word. So when the machine learns how to understand text, what it actually does internally, mathematically speaking, is it builds a better distribution of which word can fit certain place better. This way, the more powerful the model is, the closer its randomized output would be to the actual human language. So we're coming to the function of the model that can generate text. For those of you who don't know what this picture is, there's a thing called GANs, Generative Adversarial Networks, invented by Ian Goodfellow, currently at Apple. It's an awesome paper, by the way. I recommend to read it. Basically, if you have the neural net, you can reverse it and you can seed it with the random numbers and get some picture which is recognizable by this net. So when it comes to image recognition, you can also generate images from not really text, but the neurons that fired, but you get the idea. And this exploded. You can do tons of image filters on GANs. What I'm saying is probably a couple of years outdated, but this idea is catching up with text dramatically. And this is actually what I stumbled upon just a few days ago. It's an example of a subreddit. I'm not on Reddit, just taking screenshots. It's an example of the text that is generated 100% by a bot, by a machine, which is spectacular since it's kind of sophisticated. It's really hard to tell this is not a human written text, even though we know exactly how this works behind the scenes. We know exactly which bits fired, which neurons generated which words. This is where the machines are today. Impressive, huh? So any model that has some knowledge of the outer world can generate those texts. And I couldn't find the link quickly yesterday, but I remember there was a study a few years ago when Amazon built their own text model based on Amazon product reviews. What they did was It was an unsupervised solution. They took a few neurons, I think it was 128 neurons. And I think they had a single machine running for like 5 days straight, or a single cluster of a few machines. And ultimately, what they discovered after examining these neurons was that a single neuron is responsible for the sentiment of the review. So you can think of this thing, again, it's understanding versus comprehension, but it's also compression. So you can think of the Amazon product review text. When it goes through this model, it's compressed to a small number of bits, small number of neural outputs. And then you can regenerate this text with the same random seed plus this data. So what they did was they realized which neuron corresponds to the sentiment of this review. And they realized that when you tweak this neuron, when you increase the value, you can turn negative into positive when it comes to the text of the review. And it maintains the same style as if the same person wrote it. It looks a bit like what we have seen these days is the way the machine translation works. Google has released some sequence-to-sequence models where you can see that Google's machinery has pretty much designed some internal language, which is in between similar languages. So you can move a slider and it translates from language, let's say English, to one of these two similar languages or something between them. In this particular case, you can move the neuron and it's as if this review is regenerated, and you can slowly see words changing from negative to positive, even though the text is totally read as if it's the same person who read it, who wrote it. And so basically it's the right question to ask. Again, you can think of the Amazon model, you can think of OpenAI model, you can think of the Shakespeare model. If it's possible to generate the text back by means of this model, then this model has the knowledge of the text with respect to what it captured. And the model is always capturing the part of the domain of natural language that was used to train this model. For example, we have at FriendlyData, we built this English to SQL platform. So you could generate English that fits the model, but it's a different kind of English compared to what Shakespeare could write. These are two different models by design. So that's the trick to keep in mind. You always want to train the model or use a model that is closer to the domain you're going to apply it to. Otherwise, you're going to get weird results. And that's, again, speaking of machines understanding human humor, well, that's a strong AI problem, right? The model that understands humor must have something within itself that understands a lot of context about the outer world. So the jokes would make sense. Even though some nasty or really bad jokes, the machines can already not only understand, but make them because, well, they're popular enough and it's not much context. Okay, enough with the academia grade part of the talk. Let's talk about what we do with NLP in the real life. I tried to give you a somewhat ordered list of what is being done these days with NLP. It's by no means exhaustive, but it's more or less what most problems would have to do with. Text categorization. I wouldn't say it's simple, it's just the easiest formulated text. You have, let's say, a paragraph of text, or a tweet in this case, and you want to categorize it into some categories, such as is it programming or philosophy, is it politics or not, is it offensive or not. Like in my days, we used to categorize news articles, that's a couple paragraphs, and you had to tell sports from politics, or maybe finance from technology. And finance from business was, I remember, a really hard problem. It was in the Reuters corpus back in the days where Netflix was giving away $1 million for the better recommender engine. We have the structured understanding part, where what you need to do is you need to extract certain entities, certain meaning, based to a specific, tailored to a specific taxonomy with respect to what the user wants to say. So for example, if it's the Q&A answering bot, you don't have to understand the whole thing that the user is asking, but you need to know whether there is a FAQ page that answered this question, or you need to know which customer support department to route this question to. Maybe, well, this kind of systems are already installed in a lot of places. If there's a chatbot on the website, there's a good chance there is some AI-ish thing behind it. And even when it comes to call centers, if you place a voice call, if you pick up your phone and call American Airlines, there's a good chance you're going to speak to a bot. And we're slowly moving towards the era where at some cases you wouldn't even be able to tell if it's a bot or no. They're really good at pretending they're human. They used to not try to hide. Now they're slowly hiding, and they're among us. sentiment analysis. This is an entirely different problem because the output is not the structure. The output is the vector of probabilities, a simplex. You would probably have some categories of sentiments you need to capture, such as happy, sad, relaxed, irritated, you name it. They would differ from application to application. And again, you don't need to understand exactly what the user is saying, but you have some kind of training data, golden data, and you can train towards it and apply this as part of your product. Translation is a huge domain by itself. Basically, what it has to do is what it has to do with these days. Machine translation existed 30 years ago, but it was a totally different species. Right now, what is being done is what is called a sequence-to-sequence learning. So it's a deep learning model behind the scenes that is consuming the text word by word by some window. It has some attrition, memory. It keeps the state of what is important, what is left behind, what is part of the context in the previous words. It keeps this as its inner layers. And then the second model, on the other hand, which is pretty much the mirror of the first one, is generating the same text in a different language, which is pretty impressive if you ask me. So it's a text comprehension plus text generation united by something in between, and the in-between part is what's responsible for capturing the meaning. There is text summarization, which again, it's close to text generation, but slightly easier because you're allowed to use phrases from the input. It's as if you're given a paper and you have to write an abstract for that. Pretty hard if you ask me, but techniques exist. There's pronoun resolution, which again is a more structured format. It's more like, let's detect pronouns. That's kind of easy. They're fixed words. And then let's have a graph of each sentence so that the machine should be able to put the exact entity name with next to each pronoun. So if there's he, you can say it refers to me. If it's they, it's to the audience, you name it. So yeah, for example, we don't have to cover this. I was just trying to walk you slowly, slide by slide. It's the same thing I covered. And now when you actually have to solve this problem, well, there's engineering and there is data science. The data science part is determined almost 100% by the kind of the objective function you have to optimize for. The objective function defines the acceptance criteria. So always, pretty much every time you're working with data, be it NLP or anything else, ask yourself, what's the acceptance criteria? What is the perfect model? What is the terrible model? How would a human behave if the human could replace or resist the model? And there are three major kinds of objective functions, which map pretty closely to the kinds of outputs. You can have the function of that returns a probability. For example, the sentiment analysis piece, you can think of it as a classifier that tells you, that gives a yes/no answer for each particular emotion, sentiment. Multi-class, it's in many ways, it's comparable to n single class classifiers. It's just a different cost function with respect to how do you compute the log loss. But again, it's the output of your model. What you would use to compute the final accuracy is input blob of text and a vector probabilities, which sum up to 1. You can have a different kind of output, which is the text you generate. This would be translation, summarization, you name it. And you can have the third kind of output, which is some formal extract from the text, which an example here would be what we did at FriendlyData, when you had to understand the query, which is English to SQL, understand the English query and build a database query. You don't care about the sentiment in the English at all. All you care about is, can you correctly understand what is being asked with respect to which fields of which tables should be queried, which joins should be made, etc. And different kinds of acceptance criteria yield different cost functions, different objective functions. The first one is log loss, probabilities. That's pretty much what you always do. If it's a language model, it's slightly trickier to actually even formulate the acceptance criteria, but you can build, if you have enough texts. What they usually do is they use unsupervised learning. So you have tons of real English texts. So you have gigabytes and gigabytes of texts, and you can use part of that as your golden set. And the quality of you generating a text from there. So the entropy in terms of bits, how much extra input information do you need to give this model to yield the text you know is correct because it's a human written text. That's a totally different world. It's not really log-loss. And when it comes to structured understanding of text, well, that's a hardcore computer science. It's really, when it comes to parsing the graph, for example, of a sentence, you know exactly how to match a graph against the graph. You know what is a true, what is a false, what is a match, what is a miss. That's the third head of this dragon. And when it comes to implementation, well, if your problem has to do with outputting probabilities, such as sentiment analysis, you are kind of lucky, because this is the domain where it is not too hard, pragmatically speaking, to get almost on par with large companies. If you really were to measure it carefully with respect to accuracy, there's no way a small company could build something that is performing as well as Google or Facebook. But for most practical use cases, the user would not notice. We're going to be making the same mistakes, but if your goal is to figure out, hey, is this angry or not? You could just train a simple model. There are tons of ways to train models. You don't even have to use neural networks. You can use more traditional machine learning to actually get to the model that would serve your product's users. When it comes to language models, well, unless you have tons of money to spare and tons of smart data scientists, you probably don't want to be training this model by yourself. Transfer learning using a different model pre-trained for you is real. It's working out well. With images, ImageNet has solved this many years ago. With text, we're slowly getting more and more models released. Well, OpenAI hasn't released their best model yet, to the best of my knowledge, but there are plenty of competitors to choose from. So if you have to generate text by yourself, unless it's in a super hardcore robotic-ish text, take a language model and deal with it. You'll probably be okay. And if it's a hardcore computer science territory, which is what we did, I don't think there's much progress made from many years ago. We're still in the territory we've been in the Chomsky grammars, in the formal logic territory. Some people even believe that human language is just a means to program humans, and we just need to reverse engineer this programming language of humans. I don't think I buy this entirely for a couple of reasons, but this approach also yields positive results when applied sparingly. And now to the gist of my talk. I'm going to share three practical pieces of advice when it comes to you actually building NLP products. So one, again, is using pre-trained models. That's the bullet point number 2 from the previous slide. If you have to generate text, don't even try doing it yourself. Use pre-trained models. Language models, such as OpenAI models, are pretty, they are too widespread. They're applicable to too broad of the range of problems. But even for tasks such as find the best word or the best distribution of words, given the context, we have embeddings. And people tend to discount them somehow. I don't know why. Embeddings are a really powerful tool because they capture the meaning of individual words, and they capture meaning of words next to each other. And they really are pre-trained in a sense that when you're using embeddings, when you're using them correctly, you are leveraging an enormous amount of optimization time spent by the machine training those models. So at least, for God's sake, don't train them from scratch. If you want to train embeddings for your own problem, take some pre-trained embeddings. It used to be Word2Vec, then Glove. I think right now BERT is pretty much the standard. So take those models and train from there. So you save yourself tons of cycles. And yeah, for language models, I'm no expert, but there are plenty of things released. So anyways, to summarize point 1, when you can use something pre-trained, by all means do it. If you can use a pre-trained model and you are consciously making a decision not to, there's a good chance you're wasting many years and 6 to 7 digit amounts of money just to compute the same things. So don't do it. The second trick is open source. There's plenty of open source these days. When I quit big companies, it was 2012. I was shocked to realize how mature the open source toolkits are. They were always buggy, even building them was a pain. trust me, it was horrible. I really regret it. Like most people who quit big companies those years, I suffered for a couple of years just because I had to relearn this whole thing from scratch and even rebuild some things from scratch. This has improved dramatically in the past 5 years. So you can really rely on tons of open source tools. They do work. They do work really well, both for structured tasks. You can use NLTK, you can use PyText, Stanford parser is awesome. And what is even more important for the now modern, now trending deep learning based techniques, well, it's an open question whether embeddings can be called deep learning. Technically, they qualify, but when it comes to texts, I think deep learning is mostly applied to, the term deep learning is mostly applied to language generation models. But again, the deeper you have to go, the more you want to use something existing. And I have yet to find a good NLP engineer who is not an expert in modern deep learning by itself. So TensorFlow and GPUs are your friends. There's just no way. I mean, there are individual people, like at FriendlyData, we had an NLP expert who's not Chomsky by himself, but kind of close, if you ask me. Like these guys can afford to not have to know this GPU-based computations. But for all of us these days, it's a safe investment of time to learn this. And the third trick, which is what I am the least non-expert in, is what is called the grammar model. Grammar models. I'm hesitant to call them rule-based, but they actually are rule-based. So let's just say I put grammar models into the slides to make it look sexy, but fundamentally the difference is trained models versus rule-based models. And rule-based as an if then else, we've all seen these memes when modern machine learning is a bunch of if then else behind the scenes. This is not entirely true for trained neural nets, but somehow there's a stigma attached to building a bunch of rules into your system. And I think this stigma is often right, but there are plenty of tasks where it's wrong. So instead of trying to build a system that understands language in a generic way, what you often can do is work the problem from the other end. You can define ways to generate the texts in a formal way. For example, if you have, it's plain computer science, it's pure combinatorics. If you have 10 ways to start a sentence and then 10 ways to put the next part of it, and each of these 10 ways has multiple ways to phrase certain things, you can multiply those things, you can have a formal grammar, and you can have the machine that will generate you billions of different phrases, which all make sense. If you then try to map them back into your definition. And think of it as a way to use human knowledge of language to come up with this formal definition of the grammar, which you then can use to not only generate a text, but to match the text against this grammar. So it would always be low recall, but super high precision. So in our case, for example, when we really had to build high precision model, because when it comes to understanding the query into the database, you cannot be 90% correct, because if it's clause after clause after clause after clause, 0.9 raised to power 7 is already under 50%. So that's unusable. So instead, you focus on high precision and you build product methods to make sure what you're writing as a user is making sense. In our case, it was a completion and suggestions engine, which guided the user through the way to write the query. And I'm not going to go into too much detail here, but the gist is that, well, you can. One good example here is parsing the dates. It's incredible how many people think they can use a deep learning trained model to parse the date. But hey, let's look at how we used to do it in the 90s. In looking back from today, we have tons of training data. So I can give you a billion pairs of, hey, this is the date and/or time. This is the canonical representation in a JSON with certain fields. You can have this training data for an enormous amount of input-output pairs. But a school kid who knows Perl can probably do an okay job building the classifier, or building the black box that converts one into the other, because they would use regular expressions. They would come up with 15 different ways to write the date. They would parse digits as digits. They know that 02 is probably February or the second day. And there will be rules. You can think of them as hacks, and they will be hacks more or less. But if all these hacks fit 2 screens and they pass golden tests, there's probably a good enough solution. And what I'm calling for here is don't over-engineer what does not have to be over-engineered. You can just use this solution, even if it's plain good old regular expressions based. And to close on this part, a good example of where you need high precision. So you need some formality. You need rules. You can't afford to do it with a deep learning model. A good example is legal text translation. I'm not going to use sequence-to-sequence learning to translate legal from German to English because, hey, it's legal. Every comma matters. I'd much rather have a high precision, low recall model, which would have to ask a legal associate twice per sentence, what does this mean? Because that's fundamentally what legal language is. It's the formal set of rules expressed in a language, which is English or German, that is not perfectly designed to express those rules. So heck, we're not going to use machine learning for that. We're going to use rules if we have to. And product tricks, such as human in the loop, such as suggestions, such as bullets emerging there, hey, you know what, this is wrong, you can replace it, rephrase it in certain ways. That's how you get to the product, which may not be that sophisticated in terms of technology, but it goes places. And in the modern days, you don't have to be fancy. You just need to get the job done. To recap, in order to be practical, in order to pragmatically solve those problems and compete with large companies, I would suggest you look into the first three directions here. Pre-trained models, open source, and don't be shy to use rule-based good old grammars. I think it's all I have.
Thank you so much, Dima. This was very insightful. I believe we have some questions. Rishi, would you like to address them?
Absolutely. So Dima, not just that there are questions that everyone is asking, even I have a set of questions that I would like to ask. Where would you like us to begin?
Oops, so, I think you got muted.
All right, can you hear us now?
I can hear you.
All right, excellent, excellent. So there are quite a few questions out there that attendees have asked. It was an excellent, excellent, excellent presentation. I think folks who want to go deeper into analytics and data science would have thoroughly enjoyed it. And you know, one of the things that I think about a lot is the context is important, and the modern language is important. So in text analytics, one big issue is, you know, we will understand, hey, somebody gets a cold and my nose is running, right? So somebody, a human being can understand pretty easily, oh, I got a runny nose, but computers would probably tend to relate running with legs. So how do you solve for something like this?
It's a really deep question. And I would first ask, when you want to solve for this, what is your objective function? And it's not a tricky question because, for example, modern embeddings, there are techniques that would disambiguate words. So you can have automated machinery that would apply unsupervised learning on a huge corpus of texts. And it would know that running has multiple meanings. And every single time it sees the word running, it would assign probabilities to which meanings could this be. In case of running knows is a phraseology. So it's a really low recall thingy. But you can tell those things. There are better examples where the same word can mean two different things and you can easily tell one from the other. Like Apache, could be helicopter, could be an Indian tribe, could be a web server. It's not hard for the machine to be able to annotate each word Apache in the text with which one of these three meanings is more likely.
Yeah, absolutely. And a similar question is, Ibrahim Sadikov asked the question. Ibrahim was also the winner for the hackathon that ABD Society did. So his question is similar. He says, I think word embeddings are effective, but still lack in differentiating antonyms and poor getting sense of context, right? So Ibrahim, if you have more, if you want to add more to this question, feel free, and I'll bring it up to Dima. Dima, one of our attendees, he asked this question early on, Aaron Chan. Aaron asks, curious to hear from your perspective on NLP's progress in multilingual driven analysis. And then he says, For example, so this question is your perspective on NLP's progress in multilingual driven analysis. For example, the ability to review narratives that has multiple language and be able to understand enough context of it.
It's a really open-ended question. Well, let me start from the first part. So for embeddings, keep in mind, they're not designed to understand. They are designed to complete. So obviously they would pretty much treat synonyms and antonyms as fits, as matches. But that's not the weakness, that's the strength. It narrows down the search space into defining whether you're dealing with A or not A in the placeholder you're looking for. Multilingual, honestly, I'm no expert here, but I think that it's important to understand we don't have enough training data for cross-language training. And as you said, with running nose, we always bring context. We humans cannot live without context. Your upbringing, the way you were raised, what you observed around yourself, the way people used to speak around you, this all has to do with the way you perceive the words you hear or read. So when it comes to being multilingual, this context of the outer world is what the machines are horrible at. A lot of people think that, hey, we can build some kind of smart AI and then feed all the Wikipedia into it, and it would know a lot about the world of humans. But it's not true. The world of humans is not computable in Wikipedia terms. Our experiences live outside texts. So the more you artificially bring in human context into the problem, such as multilingual in this case, the more you're entering this huge space where the machines are useless. So far, this window is shrinking. The machines can do more and more. But I'm positive that you can always come up with more and more problems. But the easiest way to build a counterexample to a super smart machine these days is to give it more outer context it cannot possibly be aware of. And multilingual is just one way to do it. So the errors it would make would always be more and more sophisticated.
Gotcha. And as we know, language is a living thing, right? My teenage son comes up with all these new phrases and terms, and I'm always playing catch up with him, and I bet computers will continue to play catch up with humans. So the evolving language would always be the leading thing, right? So interesting answer, great answer there. Here's another question from Claire. Claire Gao, she wants to know a little more technical question. If high level of recall is required as one goal of the model, if the goal of the model is high level of recall, will regular expression be better than machine learning approach, generally speaking?
Well, it depends on the definition of high. Look, regular expressions are a really narrow approach. They can only do so much. But for example, again, this is not something I should be talking about too deeply, but you can use the BNF grammar. And you can use grammar where the terms it captures are not just words or collections of words united by or. They can be embeddings, or they can be parts of sentences that have the meaning, which can by itself be captured by a different kind of model. So when you want high recall, let's say you want 90% recall, there's no way you can write regular expression that is under hundreds of megabytes that would capture this, obviously, for free-form text. For dates, you could. For free-form text, it's no way. But then that's what the NLP engines in my head are for. There's multiple spaces. You can use language models, you can use sequence models, or you can use rule-based models. But rules are not mutually exclusive with embeddings. Rules can just use embeddings as the input. The approach, I believe, that is usually taken these days for these problems is hierarchical. You first apply some kind of deep learned models to parts of the sentence. So you can have some sentence graph, you can have relationships as edges between words or parts, or even parts or regions of words, so parts of sentences. And then on top of this all, you have a rule-based grammar, which fires certain paths on a fuzzy triggered condition that this sounds like an adjective and this sounds like it refers to a human, for example. This is the way to get to high recall. And again, if you want high recall and high precision, you're screwed. You have to have a human in the loop, or product ideas that guide the user to write in a way that you can that your system can understand. But if you want high recall and low precision, you can do miracles with this approach.
Absolutely. And Clara, I know you have a follow-up question, so feel free to reach out to Dima directly on LinkedIn, or feel free to route the questions through ABD Society. That'll keep so we can keep everyone posted on the answers that Dima gives. Feel free to reach out to Maithili or to other panelists. Here's one more question. We're coming up to our time, so just last one or two questions. Aniruddha Shrihati wants to know, cloud platforms like AWS and GCP offer services for building NLP applications. They provide pre-trained models, which is also very helpful for startups who do not have the access to large amounts of data. And that's something, Dima, you mentioned about during the presentation. So Aniruddha's question is, do you think these cloud services are helpful for developing real-world NLP solutions faster, or they are just good enough to start because they build the solution for anybody and everybody?
I can give you a high-level answer, but it's probably what you're looking for, Anil. Look, I do things other than NLP too. And whenever a large company introduces some framework, it will always do one thing well, but this one thing will always be narrow. So it's every single time Amazon or Google introduced something out there in the world, it was always the one-trick pony. And obviously it's designed to solve some chunk of problems which is big enough, because they need success stories. They need companies that would be built on top of this idea, so that half a year from now or a year from now, they would say, hey, look, we launched these open models and we have these companies that raise huge amounts of money or get acquired because they build these awesome projects for certain tasks. But I would say when this technology just emerges, it is usually low recall, high precision. So you really have to have a product idea that tailors specifically to these needs, or you would not be able to leverage it. There are second order benefits. If you're among the first users of this technology, you can easily get free credits, or you can easily have some support from Amazon itself. If you're willing to play this game, there's a good chance you'll succeed. But if you're only trying to see if it fits you, the default answer must be no. Because you most likely don't want to play this game. Most likely you want to reformulate your problem in a way that can be solved by other means. That's as honest as it gets. Yeah. It's same with like AutoML, right? It promises miracles, or same as Einstein from Salesforce. It can do miracles in a narrow domain. And if you're outside this domain, you will need to hire people who can pretty much rebuild this thing.
Right, absolutely. That's very well laid out, Dima. Thank you for that answer. So Dima, here's one thought that I have. You know, deepfakes is becoming a big problem. And then many companies are coming together and saying, hey, we're going to come up with a way to identify the source of this image, and that way we would know whether this is a fake, a deep fake, or actually a fair or honest picture or video. Is there a similar initiative that is needed when it comes to computer-generated text? Should we even worry about it? If the computer generates text, is it important for us to know the traceability of it?
We have to worry 100%, because had we not have to worry, OpenAI would have released the language model. I think this again is a huge question, and I can only scratch the surface barely. I think it's important when we're talking about any risk, it's important to estimate the risk profile. The risk of deepfakes as a domain of our conversation doesn't exist until we have some commonly shared idea of what are the threats. What is the worst thing that could happen? What is preventable? What is inevitable? And it's just a matter of time. So when it comes to deepfakes with videos, I think the issue was a lot smaller than it actually turned out to be, because, well, yes, you could have a video of someone saying something they wouldn't say, and it could be a politician or someone else. This has never happened so far. There was not a single news story where this became an issue. With texts, it's a lot worse because, well, doorways and other nasty things existed for decades. So like I had friends talking about this 15 years ago. Hey, news are screwed because for one plausible news article, we're going to have hundreds of spammers and scammers and you name it, generating thousands of millions of those articles, so you cannot tell true from false. So I think, if you want my opinion on this, I think the true risk profile here is how many people can buy into these faulty ideas. And my personal view is that humans are actually smart, in a sense that like newspapers didn't kill the industry and radio didn't kill the industry. We just need to give it a couple years or decades until humans realize they have to filter information carefully. And it's already happening in a sense that we trust respected journalists a lot more than what you read on the internet. And I think some kind of natural selection with information will kick in a sense that people who refuse to make this change would slowly be further and further away from the mainstream, and mainstream is the true world that actually holds. So I personally am not concerned to this degree, because I think it's a naturally vaccinating thing. Human brains would be more adjusted to this, much like with advertisements that are so good these days, but we're not zombies. We still make our own decisions on what to buy. So, but with this being said, we live in the dangerous times, and there are quite a few conflicts which just need a single spark to ignite. And in those conflicts, some means to detect threats would be helpful. I don't think this means would be installed on individual computers. I think there would be counter intelligence agencies that have to find the true sources of those bad things, but let's not go there. My point is that technology must exist, and I believe people are working on that. I just don't think I don't view this as something essential that would be with us since today forever. I think the humankind will get over it.
Yeah, and I agree with you. I think the weakest link here is not, we cannot fight it at the generation level. The weakest link is the consumer. So consumer has to be more careful and aware of it. A great answer. So coming up to one last question here, Naveen wants to know, where should a beginner begin with? NLP analytics and modeling, and improve gradually from there.
Where should a beginner begin?
Yeah, start on NLP analytics and modeling.
Well, much like with any problem in the world, which is a data problem, much like with any data problem, you should begin by defining the objective function. If your goal is to be doing NLP for a living 2 years from now and pass an interview for Google or Amazon, you know what to do. There's tons of resources. If you want to be a researcher and go write papers on this and teach, that's a different track. If you just want to make sure your skill set includes NLP, I would say the field is less mature than with algorithms. With algorithms, you have stuff like lead code, where you can just practice for a couple hours a day, and in a quarter, you kind of know everything you have to know. NLP is not as good these days, so you have to make your own choices. But there are courses. There are courses on Coursera. There are blogs. There are posts. I read the word data science on Medium. The quality is quite good. Well, ABD Society hosts awesome things. Again, I think as a personal piece of advice, if you look to kickstart your career in any way, come up with a milestone that sounds slightly outside your reach for a reasonable period of time, let's say for half a year, and see how to get there. The horizons will open up, and you always find people who would teach you something. With a bit of luck, you find people who would pay you a bit, so you can be learning and being useful and making money. The world is pretty friendly these days towards technologists like us. Fingers crossed.
Awesome. We have taken up more time than we had anticipated, Dima, but we still could not come to your opinions on the poll results. Well, we got just 2 minutes. If you want to take a quick shot at that, it'll be greatly appreciated.
I'm looking at them right now. Well, what surprises me most is that 3x, on the first question, 70% of people are hesitant to tell you if the human language is invented or discovered, but we are 3-to-1 on invented versus discovered. And I'm a firm believer that it's discovered. Like the language evolves like species. I just don't see how can this not be true. You can tell if the language, you can look at a blog post and you can tell if it's written today, 5 years ago, 10 years ago, much like Charles Darwin looked at species and could tell that these birds migrated from there. So the language changes as we speak it. I'm a native Russian speaker. I haven't been living in Russia for more than 10 years. And I can see the Russian language I know is changing as people use it year after year. So I think I can only attribute this to the audience of this webinar being more hardcore technologists than I expected. Machine translation, I think, yeah, that's pretty much what I expected. I'm assuming we're going to get there sometime, not too soon. That's consistent. OpenAI withdrawing model, I'm glad to see these results. And when it comes to human humor, you guys are too optimistic, really. Under 5 years, 25%. Under 20 years, 30%. So we are more than 50% in total that in 20 years from now, the machines would understand human humor. Like, are you so bold on the machines, or are you so bearish on humans? I cannot possibly, Elon Musk had a good podcast with Joe Rogan last week. And Elon Musk said that there's a good chance, well, it was in the context of his Neuralink, of course, and I don't have a formed opinion yet, so don't quote me on this. But he was saying that in 20 years, we may well have the technology to connect to 90% of your brain neurons and tell what their meaning is. And I think even if this is true, but Elon Musk is famous for making outrageous predictions like level 5 driving, but even if this is true, the way the humans communicate is so far from intellectual, from brain-generated neurons. You have to take into account all the hormones, all the neurotransmitters, how hungry are you, how happy you are, whether you're intoxicated in one way or the other. So there's just no way. The human always wraps around all these things. Even if you have the model that captures those things, Sheldon Cooper cannot possibly understand human humor, and machines would not be much smarter than Sheldon Cooper, quite frankly. But again, I'm happy to be proven wrong. I'm glad to have a chance to speak about this, and hopefully 5-10 years from now, we'll cross path and talk about this and laugh together. But I personally cannot possibly believe this can be a solved problem anytime soon.
That's great.
Let me add one more thing, like on this note, since we really want to end on a positive one. If you really can think of a machine that can understand our humor, this machine can replace me, and you won't be able to tell if it's me or the machine. So we're talking digital immortality. We're talking avatars of our deceased grandparents who are indistinguishable from real. This is going to happen one day, but it's not going to be 20 years from now. That's my point.
Fair enough. Excellent talk. Thank you so much, Dima, for your time. This has been great. Excellent talk. And I know there are more questions. Let's have the conversation going. And we all know Bojana is the queen of events here, so please reach out to her and Matthew and the other folks at ABD Society. But thank you so much for your attendance, making this meaningful. Dima, can't thank you enough.
Thank you, Rishi. It's a pleasure, and thanks a lot for making this happen.
Thank you, Dima. Thank you, Rishi.
Thank you, Bojana. Thank you, Matthew.
Bye-bye.
You guys take care.